Now to chapter 2 and really talk about simplifying radical expressions and delving into our square roots. Now remember, a square root will undo a perfect square. And so yeah, typically we could punch this into our calculator, the square root of 124. Now 124 is not a perfect square. So when I type in the square root of 124, it's going to give me this irrational decimal that never ends. And then you're going to end up rounding. So it's never an exact answer. It is always considered rounding. So when we are talking algebra and when we start working with a lot of our algebraic equations with radicals, we have got to have exact answers. So you're going to have to be able to take a radical and simplify it. So there's a couple different ways you can go about doing this, all right? Some people really identify perfect squares really well. Some people do not. So obviously, you know, I'm going to use a separate sheet of paper. I'm going to do a couple examples first before we delve in. So obviously the square root of 25, most of us are well aware of the fact that that is 5. Now technically it's positive 5 and negative 5, but we're only going to focus on the positive answers. Or the square root of, say, 49 is 7. Okay, however, if it's not a perfect square in there, so let's say the square root of, I don't know, 24. 24 is not a perfect square. But check this out. I can actually make the square root of 24 is the same thing as the square root of 6 times 4, because 6 times 4 is 24. And I can say this is the square root of 6 times the square root of 4. This is the same thing, whether you write them together in the radical or out as separate radical signs. So now when I take the square root of 4, I actually can do that because it is a perfect square. It is 2. This right here is square root of 6 times 2, but typically we want that number, that coefficient, to be in front of that, and so we write it as 2 times the square root of 6, and that is simplified. Okay, so try that again. Let's try another one. How about the square root of 18? Okay, the square root of 18 is the same as 9 times 2. Now, 9 is a perfect square. So this is the square root of 9 times the square root of 2, or 3 times the square root of 2. Now, that's fine and dandy, but some people really struggle saying, oh, I know that 9 goes in there, or I know that 16 goes in there, or 25, or 64, or 81, and they struggle a little bit. So I want to show you another way. Another way to do this is with prime factorization. Now, if you remember way back, prime factorization, maybe you've been shown this or not. Let's say, let's do, oh, I don't know, let's try 72. Oh, I don't want to do 72. There's too many 2's in that one. Let's say, let's just try 50. Now 50, if I take, I want to take the square root of 50. First thing I want to do is I want to rewrite 50 as a product of its primes. And so starting with 2, I know I get 50 divided by 2 is 25. I can't divide by 2. Can I divide by 3? No. Can I divide by 5? Yes. And I get 5. And then I can divide by 5 again and get 1. So my primes are, so the square root of 50 is really the square root of 2 times 5 times 5. Now, 5 times 5 is 25. So if I have 2 numbers in here, that's the same as saying 2 times 5 squared. And the square root undoes the square. So when there are 2 of the same number, I can take it out front. And so I get 5 times the square root of 2. Now, if you did it as before, I could have just written 50 and said, oh, well, 25 is a perfect square, and it's times 2, and the square root of 25 is 5, and times the square root of 2, you get the same answer. But remember, you don't always have to do it the same way. Okay, that being said, let's look at this one. 124. I am not sure. I'm pretty sure that 4 goes into 124. And it does, so this is the same as 4 times 31. Now I also am pretty familiar with my prime numbers, and I know 31's prime number. So I can take the square root of 4, which is 2, but I'm going to leave the 31 alone because it's prime. There's nothing else that comes out. There's definitely not a perfect square that comes out of there. Okay, moving on to the square root of 80. Now how many of you know what perfect square goes into 80? 16, yeah, because 16 times 5 is 80. So I could write this as 16 times 5. Well, the square root of 16 is 4. And the 5 stays in the square root. So we can simplify square roots or radicals into something easier. All right, now if we have a product, now if we're multiplying two radicals, so if we zoom in here on example number 2, if they're both under the radical sign, there you go, refocus, come on. If they're both under the radical sign, you would simply multiply them out. But I'm going to let you in on a secret. I know that 18 has a perfect square in there. How many of you saw that coming? This is the square root of 5, and this is 9 times 2. Okay, now I could rewrite this as the square root of 5 times 9 times 2, but 9 is a perfect square. What is the square root of 9? 3. So I can take a 3 out, and I have 5 times 2 in there. I can't take anything else out, so 5 times 2 then is 10, and that's as simplified as I get. Now let's say it's a radical with a coefficient out in front, like a mixed radical. I can take 2 times 3, I can take the numbers out front and multiply them, and that gives me 6. But inside, I could take 6 times 8, but I'm just going to leave it like this. Because, well, you know what? Let's just go ahead and do that. 6 times 8 would be 48. And what perfect square goes into 48? How many of you know? It is 16. Do you know how many times 16 goes into 48? 3. So 16 times 3 gives me 48. The square root of 16 is 4. So when I take a 4 out, if there's already a number out front, I have to multiply them. So 6 times 4 is 24, and times the square root of 3. All right? Moving on now, on your notes, this does not, it's not complete right here. And I'm not gonna sugarcoat it. This to me was a confusing concept. Okay, because if I take the square root of, remember, if we take the square root of 16, it is a positive or a negative 4. There are 2 possible answers. Now, we only want the positive answer. So that's why right here you see this is x squared, you know, so 4 squared equals this, it would be 4. But they put the absolute value so that they understand that it has to be a positive answer. They can't have a negative answer because you can't take a square root of a negative number. Actually, that doesn't matter. But so when you take out an x squared, on the square root will undo the square, but if you have an odd exponent out here, you have to include the absolute value bars. So x cubed is like x squared times x. So you can take this one out, that's where this comes from, and then you have to leave the single one in there. All right? And then so on. X to the 4th is 2x squared, so we got x squared and x squared, so you can take out 2 of them. That's why x squared is out here. And so on and so forth. You must use the even and simplified exponent is that. You must use the absolute value. All right? So, even and it ends up being odd. Even and it ends up being odd, you have to use the absolute value. And just follow along. You'll get it. So let's flip this baby over. And now we are simplifying not just numbers, but now we've got variables in there too. So first thing let's focus on is the 27. Now I know 27 is 9 times 3. And then a to the 5th is a to the 4th and a. And then we have a b, and then we have c squared. Now why did I separate the a to the 4th and a? Well, you'll see in a minute. The 9 is a perfect square. So what's the square root of 9? 3. All right, and so I'm taking that out front. All right, the 3 has to stay. The a to the 4th is a perfect square. A perfect square of what? A squared. So I'm taking that out front. The single a has to stay. The single b has to stay. The c squared is a perfect square of c, but it went from an even and I got an odd, so I need the absolute value out here. But don't forget, I still have the 3, the a, and the b inside. So I have 3a squared absolute value of c equals the square root of, sorry, doesn't equal, oh my bad, 3a squared absolute value of c times the square root of 3ab. I made my little tail a little longer than I needed to. Okay, while we're pondering that, you can reverse it and watch it again, or I'm going to keep going. I'm going to simplify. Now, 90, 9 and 10. All right, 9 and 10. I'm going to change the x to the 3rd to x squared times x because I want a perfect square. Y to the 4th is a perfect square. Z to the 5th, I'm going to make 4 and 1. So now I'm going to take out the perfect squares. 9 is a perfect square of 3. X squared is a perfect square of 1, and I need absolute values. Y to the 4th is a perfect square of y squared, and z to the 4th is a perfect square of z squared. So those two I took out, leaving me with 3 absolute value of x, y squared, z squared, times the square root of 10 x, z. Almost more complicated, and you're probably not going to get one like that where you have to simplify in your problem, but we're practicing the simplifying procedure. So while this is probably more hideous to look at than the other one was, there is a rhyme or reason. We're practicing. Okay, let's try this next one. 56. What perfect square goes into 56? Anybody know? I know 4 does. I think that is it. Yeah, okay. So 56 is 4 times 14. Why 4? Because 4 is a perfect square. All right, then x, I'm just going to leave as x. Y to the 10th, there's another perfect square. But I'm going to change the z to the 5th to a z to the 4th and a single z. Why do I do that? Because now I'm going to take out my perfect squares. Perfect square of 4 is 2. Perfect square of square root of y to the 10th is y to the 5th. Went from an even exponent to an odd, so I need absolute value. And then z to the 4th is going to be z squared, and I'm taking that one out, and I took that one out. So now I have 2 times the absolute value of y to the 5th, z squared, and in my square root, I still have 14xz. And you simplify that out. Okay, simplifying radicals. Now the other thing with simplifying radicals is that we, when we have fractions involved, cannot have a radical, a square root in the denominator of a fraction. So this is going to seem weird, but here's because it's the square root of 5. In order to get rid of the square root of 5, I'm going to multiply both the numerator and the denominator, because whatever I do to the top, I got to do to the bottom. Otherwise, because this is just multiplying by 1. So I'm going to multiply them by the square root of 5. You're probably thinking, why are you multiplying by the square root of 5, Mrs. Barsh? Well, I'll tell you. Well, the top is kind of ugly. The bottom, square root of 5, would be the square root of 25, because 5 times 5 is 25. And what is the square root of 25? Yes, it's 5. So now, while I have, a radical that is now in the numerator, what I don't have is 1 in the denominator, and that is what I wanted. I cannot have a radical in the denominator of a fraction. I have to rewrite it like this. Okay, let's try one just a step harder. In this one, you'll see that there's a radical in both the top and the bottom, and you're probably thinking, oh, multiply by the square root of 20. You could, but I'm going to make it a little bit easier. All right, because they're both under the radical sign and they're both even, I'm actually going to factor out a 2. So I'm going to simplify it down to now I have 7x on the numerator, square root of 7x, and in the denominator I have the square root of 10. So now I got littler numbers to deal with. I always recommend doing that. And now you can take them times the square root of 10 over the square root of 10. In the numerator, kind of ugly, square root of 70x. In the denominator, 10. Now, we also have to think, can we factor anything? Is there any perfect squares I can take out of 70? Well, 2 is not, so 1, that doesn't help me. So 4 does not go into 70. 9 does not go into 70. 16 does not go into 70. 25 does not go into 70. 36 does not go into 70. And I'm basically done. It's not going to simplify down anymore. As ugly as it is, that is the simplified answer. All right, so next, top of the next page, we're just going to go a step harder. This is going to be our last example for today. You'll see the radical in this one actually covers the whole thing. That is the same as saying the square root of 4y over the square root of 3y, and I'm actually going to separate that. Y times y is y squared. Why did I separate it? Because I'm going to simplify before I start getting rid of my radical. Because I got a y in the numerator and in the denominator. I can actually simplify one of those out. And so now I just have, oh, the square root of 4. Wait a minute, what's that? 2 in the numerator, and in the denominator, the square root of 3y. So now I multiply by the square root of 3y over the square root of 3y.
Mr. Parks, please call the front office. Mr. Parks.
And in the denominator, I'm going to get 3 absolute value of y. And in the numerator, 2 square root of 3y. There again, this is technically the square root of 9y squared. And when I take the square root of y squared, I have to have an even number of exponent goes to a single. We need the absolute value bars. All right. Okay, so moving on, this is actually where we are going to stop. We're going to do some more examples on the back of this sheet just for example have you. And then your assignment will be just the front side. We will talk about conjugates and simplifying these, which are a little bit more complicated, tomorrow. We will do that so we can simplify. We'll come back to this tomorrow, and you can go to the back side because you know what? We're going to practice this. Understanding, here it is, when we need the absolute value and when we don't. So we'll look. We have an even x squared, an even exponent, and when I take that out, I'm going to get a single exponent, so I need the absolute value of the x. And I can take a y, I'm going to change the y to y squared and y, so I can take out one of them, and inside I just get a y. So why am I not putting the y out front in absolute value? Because it started with a 3 exponent. So I don't have to. It only goes if you start with an even and end with an odd exponent. All right, so same thing. X squared, I can take out that, and I'm going to get the absolute value of x because even, and it ends up with an odd, which is 1. Now y to the 4th is a perfect square, but it's the perfect square of y squared. So even though I started with an even exponent, when I took the square root, I ended with an even. So I don't need the absolute value for that. Okay, moving on. X to the 3rd, y to the 5th. Guess what? No absolute value necessary here because they didn't even start with even exponents. All right, now I'm just going to rewrite it as x squared times x and y to the 4th times y. Why do I do that? Well, because I could take out this one of those and 2 of those. So I got x, y squared, and what am I left with? X, y inside. Keep going right here. Again, starting with odd exponents, so I don't have to worry about that. This one's going to be x to the 4th, y squared, and inside x, y. And last but not least, again, no evens. So no absolute value necessary. And so I can take an x squared out, I can take a y squared out, and I'm left with xy inside. Okay, so I hope that helps. So your assignment is the front side. Oh, I don't have it with me. The front side. It says day 1 on it. Make sure you come see me if you have any questions. I think you guys are in good hands. All right, and we will continue this lesson on this back sheet tomorrow, dealing with rationalizing the denominators when it's a binomial, 2 terms down there as opposed to just 1. Okay, see you tomorrow.